Yonghui He, welcome to the podcast. I'm so excited to speak with you. You have an energetic humility, and your expertise and your passion comes across whenever I watch any of your lectures. So it's an honor.
It's a great pleasure and great honor to be here. In fact, I'm a great admirer of yours. You've interviewed several of my very distinguished colleagues, like Roger Penrose and Eric Frankel. I watched some of them, and it's actually really nice.
Wonderful, wonderful. Well, that's humbling to hear. So firstly, people should know that we're going to talk about, or you're going to give a presentation on AI and machine learning mathematics and the relationship between them,
Right.
as well as the three different levels of what math is in terms of production and understanding, bottom up, top down, and then the meta. But prior to that, what specific math and physics disciplines initially sparked your interest? And how did the collaboration with Roger come about?
So my bread and butter was mathematical physics, especially sort of the interface between algebraic geometry and string theory. So that's my background, what I did my PhD on, and so at some point I was editing a book with C.N. Yang, who is an absolute legend. He's 102. He's still alive, and
Yes.
is the world's oldest living Nobel laureate. Penrose is a mere 93 or something. So C.N. Yang of the Yang-Mills theory, so it's an absolute legend. He got the Nobel Prize in 1957. So at some point, I got involved in editing a book with C.N. called Topology in Physics. And, with a name like that, you can just invite anybody you want, and they'll probably say yes. And that was my initial friendship with Roger Penrose started through working together on that editorial. I mean, I have Roger as a colleague in Oxford, and I've known him on and off for a number of years, but that's when we really started working together.
So when Roger snickers at string theorists, what do you say? What do you do? How does that make you feel?
That's totally fine. I mean, I'm not a diehard string theorist, and I'm just generally interested in the interface between mathematics and physics. And Roger's totally chill with that.
So you just happen to study the mathematics that would be interesting to string theorists, though you're not one.
Exactly, and vice versa. I just completely chanced on this. It was kind of interesting. I was recently given a talk, a public lecture in Dublin about the interactions between physics and mathematics. And I still find that string theory is still very much a field that gives the best cross-disciplinary, kind of feedback. And it's been doing that for decades. It's a fun thing. I talk to my friends in pure mathematics, especially in algebraic geometry. 100% of them are convinced that string theory is correct, because for them it's inconceivable for a physics theory to give so much interest in mathematics.
Interesting.
And that's kind of I think that's a story that hasn't been told so much, in media. If you talk to a physicist, they were like, string theory doesn't predict anything, this and the other thing. But there's a big chapter of string theory. To me, more than 50% of the backstory of string theory is just constantly giving new ideas in mathematics. And historically, when a physical theory does that, it's very unlikely for it to be completely wrong.
Yeah. You watch the podcast with Edward Frankel, and he takes the opposite view, although he initially took the former view that, okay, string theory must be on the correct track because of the positive externalities. It's like the opposite of fossil fuels. Right. It doesn't give you what you want for your field, like physics, but it gives you what you want for other fields as serendipitous outgrowth. But then he's no longer convinced after being at a string conference. So you still feel like the pure mathematicians that you interact with see string theory as on the correct track as a physical theory, not just as a mathematical theory.
Yeah, so absolutely. He does make a good point. And so, I think, Frankel and, algebraic geometrists like Richard Thomas and various people, they appreciate what string theory is constantly doing in terms of the mathematics. And the challenge is, whether it is a theory of physics based on the fact that it's giving so much mathematics. I guess you got to be a mystic. Some of them are mystics. Some of us are mystics. And I don't personally have an opinion on that. I just some days I'm like, well, this is such a cool mathematical structure, and there's so much internal consistency. It's got to there's got to be something there. So it's just a gut
Uh-huh.
feeling. But of course, it being a science, you need the experimental evidence. You need to go through the scientific process, and that I have absolutely no idea. It could take years and decades.
Wouldn't you also have to weight the field, like WEIGHT, weight the whatever field, like the subdiscipline of string theory, with how much IQ power has been poured into it, how much raw talent has been poured into it versus others? So you would imagine that if it was the big daddy field, which it happens to be, that it should produce more and more insights. And it's unclear to me, at least, if that this much time and effort went into asymptotic safety or loop quantum gravity or what have you, or causal set theory, if that would produce mathematical insights of the same level of quality. We don't have a comparison. I mean, I don't know. I want to know what your thoughts are on that.
I think the reason for that is just that we follow our nose as a community, and the contending theories like loop quantum gravity and stuff. There are people who do it. There are communities of people who do it, and there's a reason why the top mathematicians are doing string related stuff. It's because you follow the right nodes. You feel like it is actually giving the kind of the right mathematics. Things like mirror symmetry, or vertex algebras. That's kind of giving the right ideas constantly, and it's been doing this since the very beginning. So, and people do, the other alternative theories of everything, but so far it hasn't produced new math. You can certainly prove us wrong, but I think I follow. There's a reason why Witten is the one who gets the Fields Medal, because it's just somehow is at the right interface of the right ideas in geometry, number theory, representation theory, algebra. That this idea tends to produce the right, the right mathematics. Whether it is a theory of physics, that's still that's the next mystical level. But it's kind of it's an exciting time, actually.
Witten didn't get the Fields Medal for string theory, though. It was his work on the Jones polynomial and Chern-Simons theory and Morse theory with supersymmetry and topological quantum field theory, but not specifically string theory.
That's right. But he certainly is a champion for string theory. And for him, I mean, that idea of funny. So he was able to do, the Morse theory stuff. He was able to get because of his work on supersymmetry. He was able to realize this was some supersymmetric index theorem that generated this idea, and that's really supersymmetry really is a cornerstone for string theory, even though there's no experimental evidence for it. So I think that's one of the reasons that's guiding him towards this direction.
So what's cool is that the podcast that I filmed just prior to yours was Peter Woit, as you know, is a critic of string theory, and Joseph Conlin, who is a defender of string theory, and he has a book even called Why String Theory.
That's right.
I think it was the first time that publicly someone like Peter Woit, along with a defender of string theory, were just on a podcast of this length speaking about in a technical manner what are both of their likes and dislikes of string theory and then the string community. There's three issues: string theory as a physical theory, string theory as a tool for mathematical insight, and then three, string theory as a sociological phenomenon of overhype, and does it see itself as the only game in town? Is there arrogance? Should there be arrogance? It was an interesting conversation.
Yeah. Well, Joe is a good friend of mine, Joe Conlin.
Yeah, right, in Oxford.
And I value his comments greatly. I've always been kind of, for me, so I've always been kind of like slightly orthogonal to the main string theory community. I'm just happy because he's constantly giving me good problems to work on.
Yes,
including what I'm about to talk about in AI.
Wonderful.
And I'll mention a little bit about it because I got into this precisely because I had a huge database of Calabi-Yau manifolds, and I wouldn't have done that without the string community. It's again one of those accidents that no other, the other theoretical physicists didn't happen to have this. Didn't happen to be thinking about this problem. There's this proliferation of Calabi-Yau manifolds, and I'll mention that bit in my lecture later, and why this is such an interesting problem, why Calabi-Yauness is interesting inherently, regardless whether you're a string theorist. And that kind of launched me in this direction of AI-assisted mathematical discovery. So this is kind of really nice, and I think I mean, for me, the most exciting thing about this whole community is that, you know, science and, you know, and especially, you know, theoretical science, well no, not especially science, including theoretical science, has become so compartmentalized, right? You know, everyone is doing this tiny little bit of thing, and and string theory has been breaking that mold for the last decades. It's constantly going, let's take a piece of algebraic geometry. Let's take a bit of number theory here, elliptic curves. Let's take a bit of quantum information, entanglement, whatever, entropy, black holes. And it's the only field that I know that different expertise are talking to each other. I mean, this doesn't happen in any other field that I know of in sort of mathematics, theoretical physics. And that just gets me excited. And that's what I really like thinking about.
Well, let's hear more about what you like thinking about and what you're enthusiastic about these days. Let's get to the presentation.
Sure. Well, thank you very much for having me here. And I'm going to talk about work I've been thinking about, stuff I've been thinking about for the last 7 years, which is how AI can help us do mathematical discovery, you know, in theoretical physics and pure mathematics. I recently wrote this review for Nature, which is trying to summarize a lot of these ideas that I've been thinking about. And there's an earlier review that I wrote in 2021 about, you know, how machine learning can help us with understanding mathematics. So let me just take it away and think about. Oh, by the way, please feel free to interrupt me. I know this is one of those lectures. I always like to make my lectures interactive. So please, if you have any questions, just interrupt me anytime, and I'll just pretend there's a big audience out there, and I'll just make it.
So firstly, you're likely going to get to this, but what's the definition of meta mathematics?
Okay, great. So, roughly, of course, you know, how does one, so the first question is, how does one actually do mathematics, right? And so one can think about, of course, these, in these reviews, I try to divide it into sort of 3 directions. Of course, these 3 directions are interlaced, and it's very hard to pull them apart. But roughly, you can think about, you know, bottom-up mathematics, which is, you know, mathematics is a formal logical system, you know, definition and, you know, lemma, proof, and, you know, theorem, proof.
Mm-hmm.
And that's certainly how mathematics is presented in you know, papers. And there's another one which I like to call top-down mathematics, is where, you know, where the practitioner looks from, you know, above. That's why I say top-down, from like a bird's eye view. You see different ideas and subfields of mathematics, and you try to do this as a sort of an intuitive, creative art. You know, you got some experience, and then you're trying to see, oh, well, maybe I can take a little bit of piece from here and a piece from there, and I'm trying to create a new idea, or maybe a method of proof or attack or derivation.
Yes.
So these 2. So that's you know, so complementary directions of research. And the third one, meta, that's just because it was short of any other creative words, because there's, you know, words like meta science and meta philosophy or metaphysics. I'm just thinking about mathematics as purely as a language, you know, whether the person understands what's going on underneath is of secondary importance. So it's kind of like ChatGPT, if you wish. You know, can you do mathematics purely by symbol processing? So that's what I mean meta. So I'm going to talk a little bit about, in this talk, about each of the 3 directions, and focusing mostly on the second direction of top-down, which is what I've been thinking about for the last 7 years or so.
Okay, I don't know if you know of this experiment called the Chinese room experiment.
Yeah.
Okay, so in that, the person in the center who doesn't actually understand Chinese, but is just symbol pushing or pattern matching, I don't know if it's exactly pattern, rule following, that would be the better way of saying it.
Yeah.
They would be an example of bottom up or meta in this.
So I would say that's meta.
As you know, on Theories of Everything, we delve into some of the most reality spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in. And now back to our explorations of the mysteries of the universe.
So I would say that's meta, in the sense that the person doesn't even have to be a mathematician. You're just simply taking symbols, large language modeling for math, if you wish.
Got it.
Yeah. Of course, there's a bit of component of others, that you can see there's a little bit of component of bottom up, because you are taking mathematics as, a sequence of symbols. But I would mainly call that meta, if that's okay. I mean, these definitions are just, things that I'm using.
Yes.
But in any case, I would talk mostly about this bit, which is this, what I've been thinking mostly about. One thing I just to set the scene, 20th century, of course, computers have been playing an increasingly important role in mathematical discovery. Right? And of course, it speeds up computation, all that stuff goes without saying. But something that's perhaps not so emphasized and appreciated is the fact that there are actually fundamental and major results in mathematics that could no longer have been done without the help of the computer. And so this, there's famous examples. Even back in 1976, this is the famous Appel-Haken-Koch proof of the four-color theorem. That every map, every map in a plane only takes 4 colors to completely color it with no neighbors. And this is a problem.
Mhm.
This is a problem that was posed, I think, probably by Euler, right? And this was finally settled by reducing this whole topology problem to thousands of cases, and then they ran it through a computer and checked it case by case. So, and then other major things like, the Kepler conjecture, which is, that stacking balls, identical balls. The best way to stack it is what you see in the supermarket, in this hexagonal thing. And this was conjectured by Kepler, but to prove that this is actually the best way to do it, was settled in 1998, again by huge computer check. And the full acceptance by the math community, it was only as late as 2017 when proof co-pilots actually went through Hales's construction and then made this into proof.
Yes. But wasn't there a recent breakthrough in the generalized Kepler conjecture?
Absolutely. So this is what Marina Wiercowska got the Fields Medal for, so the Kepler conjecture is in 3 dimensions, where, our world. Wiercowska showed in dimensions 8, 16, and 24 what the best possible packing are. And she gave a beautiful proof of that fact. And I, to my knowledge, I don't think she actually used the computer. There's some optimization method.
Actually, what I'm referring to is that there's some researchers who generalize this for any n, not just 8, not just 24, who used methods in graph theory of selecting edges to maximize packing density to solve the sphere packing problem probabilistically for any n. Though I don't believe they used machine learning.
Oh, thanks for telling. And I've got to check that. That's interesting. This was actually really interesting one. Is the classification? I mean, that's something that's closer to me, which is the classification of finite simple groups. So simple groups are building blocks of all finite groups, and the proof is, took 200 years. And the final definitive volume was by Gorenstein 2008. And what's really interesting, the lore in the finite group theory community, is that nobody's actually read the entire proof. It's just not possible. It takes longer for people to actually read the entire proof than a lifetime of, than a lifetime. So this is kind of interesting that, we have reached the cusp in mathematical research where mathematics, the computers are not just becoming, computational tools, but it's increasingly becoming an integral part of who we are. So this is just just set the scene. So we're very much in this, we're now in the early stages of the 21st century, and this is increasingly the case where we have this, where computers can help us, or AI can help us in these three different directions.
Great.
So let me just begin with this bottom up, and sort of to summarize this. This is probably the oldest attempt in where computers can help us. So this is where I'm going to define bottom up, which is, I guess it goes back to the modern version of this is this classic paper, the classic book of Russell Whitehead on the Principia Mathematica, which is 1910s, where they try to axiomatize mathematics, from the very beginning. It took like 300 pages for them to prove that 1 + 1 is equal to 2, famously. Nobody has read this. So this is one of these impenetrable books. But this tradition goes back to, Leibniz or to Euclid even, that the idea that mathematics should be axiomatized, right? Of course, this program took only about 20 years before it was completely killed in some sense, because of Gödel and Church and Turing's incompleteness theorems. That this very idea of trying to axiomatize mathematics by constructing layer by layer is proven to be logically impossible within every order of logic. But I like to quote my very distinguished colleague, Professor Min-Young Kim. He says the practicing mathematician hardly ever worries about Gödel, because if you have to worry about whether your axioms are valid to your day to day, if an algebraic geometer has to worry about this, then you're sunk, right? Then you get depressed about everything you do, right? So the two buts kind of cancel out. But the reason I mention this is that because of the fact that these two buts cancel each other out, these two negatives cancel each other out, this idea of using computers to check proofs, or to computer-aided proofs, really goes back to the 1950s, right? So despite the what Gödel and Church and Turing have proved, which is foundational, even back in 1956, Noah, Simon, and Shaw devised this logical theory machine. I have no idea how they did it, because this is really very, very, very primitive computers. And they were actually able to prove some certain theorems of Principia by building this bottom-up, take these axioms and use the computer to prove. And this is becoming, an entire field of itself, with this very distinguished history. And just to mention that this 1956 is actually a very interesting year, because it's the same year, 56, 57, that the first neural networks emerged from the basement of Penn and MIT. And that's really interesting, right? So people in the 50s were really thinking about the beginnings of AI, because neural networks is what we now call, goes under the rubric of AI. And at the same time, they were really thinking about computers to prove theorems in mathematics. So 56 was a kind of a magical year. And, this neural network really was a neural network, in the sense that, they put cadmium sulfide cells in a basement. It's a wall size of photoreceptors. And they were using, flashlights to try to stimulate neurons, literally to try to simulate computation.
Uh-huh.
Well, that's quite an impressive thing. And then this thing really developed, right? And then and now half a century later, we have very advanced and very, very sophisticated computer aided proof, automated theorem provers, things like the Coq system, the Lean system. And they were able to create. So Coq was what was used in this four-color. The full verification of the proof of the four-color theorem was through the Coq system. And then there's the Phi-Thompson theorem, which got Thomson the Fields Medal. Again, they got the proof through this system. And Lean is very good. I do a little bit of Lean, but also Lean. The true champion of Lean is Kevin Buzzard at Imperial, 30 minutes down the road from here, from this spot. And he's been very much a champion for what he calls the Xena project, and using Lean to formalize all of mathematics. I mean, that's the dream. And what Lean has done now is that it has, Kevin tells me that all of the undergraduate level mathematics at Imperial, which is a non-trivial set of mathematics, but still a very, very tiny bit of actual mathematics. And they can check it, and everything that we've been taught so far at undergraduate level is good and self-consistent, so nobody needs to cry about that one.
Wonderful.
And so that's all good. And then more recent breakthroughs is the beautiful work of, so 3 Fields medalists here. Also, two Fields medalists, Gowers Green, Manners, and Tao, Manners, I think it's an S, and Tao, where they proved this conjecture, which I don't know the details of, but they were actually using Lean to prove, to help proving this. And I think Terry Tao, in this public lecture which he gave recently in 2024 in Oxford, he calls this whole idea of AI co-pilot, which I very much like this word. I was with Tao in August in Spain, in Barcelona. We were at this conference, and he's very much into this very well. And of course, Terry Tao for us is a godlike figure. So, and the fact that he's championing this idea of AI co-pilots for mathematics is very, very encouraging for all of us.
Yes, and for people who are unfamiliar with Terry Tao, but are familiar with Ed Witten, Terry Tao is considered the Ed Witten of math, and Ed Witten is considered the Terry Tao of physics.
Yeah, I've never heard that expression. That's kind of interesting. At Barcelona, when Terry was being introduced by the organizer, Eva Miranda, she said, Terry Tao is, this is a very beautiful sentence, Terry Tao has been described as the Gauss of
Yes.
mathematics.
Or the Mozart.
But I think a more appropriate thing to describe him is to describe him as the Leonardo da Vinci of mathematics, because he has such a broad impact on all fields of mathematics, and that's a very rare thing.
Yeah, I remember he said something like, topology is my weakest field. And by weakest field to him, it means I can only write 1 or 2 graduate textbooks off of the top of my head on the subject of topology.
Yeah, exactly. I guess he's very, his intuitions are more analytic. He's very much in that world of analytic number theory, functional analysis. He's not very pictorial, surprisingly. Like Roger Penrose has to do everything has to be in terms of pictures, but Terry is a symbolic matcher. We can just look at equations, extremely long, complicated equations, and just see which pieces should go together. That's kind of very interesting.
Speaking of Eva Miranda, you and we have several lines of connection. Eva's coming on the podcast in a week or 2 to talk about geometric quantization.
Awesome. Well, Eva is super fun, right? She's filled with energy.
Yes.
Yeah, she's a good friend of mine. Yeah. I think, in this academic world of, math and physics, I think, we're at most 1 degree of separation from anyone else. Yeah. It's a very small community, relatively small community. So back to this thing about, and of course, one could get over optimistic. I was told by my friends in DeepMind that Szegedy, who I think he's one of the on this AI math team. He says, he was extracting that computers beat humans in chess in the 90s, beat humans Go at 2018. So you should beat humans in beating proving theorems in 2030. I have no idea how he extrapolated these 2 points. Only 3 data points, but DeepMind has a product to sell, so it's very good for them to be over optimistic. But I wouldn't be surprised that this number, I'm not sure it'll beat humans, but it might give ideas that humans have not thought about before. So that's possible. Just moving on. So that's the bottom up, and I said this is very much a blossoming, or not blossoming, it's very much a long distinguished field of automated theorem computing, of theorem provers and verifications of formalization mathematics, which Tao calls the AI co-pilot. Just to mention a bit with your question a bit earlier about meta mathematics. Right? So this is just kind of, I like your analogy. This is like the Chinese room. Right? Can you do mathematics without actually understanding anything? Personally, I'm a little biased because having interacted with so many undergraduate students before I moved to the London Institute, so I don't have to teach anymore, or teach undergraduates. I've noticed, maybe one can say the vast majority of undergraduates are just pattern matching.
Right.
Whether there's any understanding, I think this is one of the reasons why why ChatGPT does things so well. It's not because oh, LLMs are great, large language models are great. It's more that most things that humans do are so without comprehension anyway. So that's why it's kind of this pattern matching idea. And this is also true for mathematics.
What's funny is that my brother's a professor of math in the University of Toronto for machine learning, but for finance. And I recall 10 years ago, he would lament to me students that came to him who wanted to be PhD students, and he would say, okay, but Kurt, some of them, they don't have an understanding. They have a pattern matching understanding. He didn't want that at the time, but now he's into machine learning, which is effectively that times 10 to the power of 10.
Right. Right. No, I completely agree. I mean, this is not to criticize undergraduate studies. I think in undergraduate students, it's just that it's part of being human. We kind of pattern match, and then we do it the best we can. And then, of course, if you're Terry Tao, you actually understand what you're doing. But
of course,
but the vast majority of us doing most of the stuff is just pattern matching. So that's why, and this is true even for mathematics. So here I just want to mention something, which is a fun project that I did with my friends Vishnu Jujala and Brent Nelson back in 2018, before LLMs, before all this LLM for science thing, and this is a very fun thing because what we did, we took the archive and we took all the titles of the archive. This is the preprint server for contemporary research in theoretical sciences. And, we were doing LLM classifiers, Word2Vec, very old-fashioned. This is a neural network, Word2Vec. Mm-hmm. And, you can classify this and do their thing. But what's really interesting, this is my favorite bit, we took, to benchmark the archive, we took Vixra. So Vixra is a very interesting repository because it's archive spelled backwards. And it has all kinds of crazy stuff. I'm not saying everything on Vixra is crazy, but certainly it has everything that archive rejects because he thinks it's crazy. Things like, 3-page proof of the Riemann hypothesis, or Albert Einstein is wrong. It's got filled with that. And it's interesting to study the linguistics, even at a title level. You could see that, what they call the distinctions of quantum gravity versus the other things, they have the right words in Vixra, but the word order is already quite random. In other words, the classification matrix, the confusion matrix for Vixra is certainly not as distinct as archive, which, so kind of interesting, you get all the right buzzwords. It's like, kind of thing, Vixra, I think, is a good benchmark. Linguistically, it's not as sophisticated as, real research articles. But this idea, so this is something much more serious. It's this very beautiful work of Chitoyan et al. In Nature, where they actually took all of material science and they did a large language model for that, and they were able to actually generate new reactions in material science. So I think this paper in 2019, this paper by Chitoyan is really the beginnings of LLM for scientific discovery. This is quite early. This is 2019, right?
Yeah. And it's remarkable how we can even say that that's quite early. The field is exploding so quickly.
Absolutely.
That 5 years ago is considered quite some time ago.
Right.
Yeah.
Absolutely. Even 5 years ago, I was still very much in a lot of. I've evolved in thinking a lot about this thing.
I would also like to get to your personal use cases for LLMs, ChatGPT, Claude, and what you see as the pros and cons between the different sorts. Like Gemini was just released at 2.0. And then there's 01, and there's a variety. So at some point, I would like to get to you personally, how you use LLMs, both as a researcher and then your personal use cases.
Well, I can mention a little bit. So one of the very, very first things when ChatGPT 3 came out in 2018, 2019, something like that?
ChatGPT, 3. You mean GPT-3?
GPT-3, like the really early baby versions.
Yeah, that was just before the pandemic.
Just before pandemic. So that was just like, so I got into this AI for math through this Calabi-Yau manifold, which I'm going to mention a bit later. And then this, and GPT came out when I was just thinking about this large language model. So this is a great conversation. So I was typing problems in calculus, right? Freshman calculus. and it will solve that, fairly well. I mean, it's really quite impressive what he can do. So, it is fairly sophisticated because, things like, I was typing questions like, take vector fields, blah blah blah, on a sphere, find me the grad or the curl. I mean, it's like, first, second year stuff, and you have to do a lot of computation. And he was actually doing this kind of thing correctly, partially because there's just so many example sheets of this type out there on the internet, and so he's kind of learned all of that. So I was getting very excited, and I was trying to sell this to everybody at lunch. I was having lunch with my usual team of colleagues in Oxford over this, and of course, lo and behold, who was at lunch is the great Andrew Wiles.
Mm.
And so I felt like I was being a peddler for GPT, LLM for mathematics, to perhaps the greatest living legend in mathematics. And Andrew's super nice, and he's a lovely guy, and he just instantly asked me, he says, "How about you try something much simpler?" Two problems he tried. The first one was, tell me the rank of a certain elliptic curve, and he just typed it down, a certain elliptic curve, or rational points of a very simple elliptic curve, which is his baby. And I typed it in one. It got completely wrong.
Yes.
It was just he started saying things like, 5/7 is an integer. Partially because this is a very hard thing to do. You can't really guess integer points by just, unlike in calculus where there's a routine of what you need to do, right? And then very quickly we converged on an even simpler problem. How about find the 17th digit in the decimal expansion of 22 divided by 29, like whatever. And that it's completely random because you can't train it. You actually have to do long division. This is primary school level stuff. And yet GPT just simply cannot do. And it's inconceivable that it could do it because no language model could possibly do this. But GPT now, 001, 02, 01 is already clever enough. When you ask him a question like this, linguistically, it knows to go to Wolfram Alpha. And then it's okay. Then it's actually doing the math. But so something so basic like this, you just can't train a language model to do. You get, 1 in 10 right. And it's just a randomly distributed thing.
Yes.
Whereas sophisticated things, seemingly sophisticated things like solving differential equations or doing very complicated integrals, it can do because there's somewhat of a routine and there are enough samples out there. So anyhow, that's my use case, 2 use cases.
That's also not terribly different than the way that you and I, or the average person, or people in general, think. So, for instance, we're speaking right now in terms of conversation. And then if we ask each other a math question, we move to a math part of our brain. We recognize this is a math question. So there's some modularity in terms of how we think. It's not like we're going to solve long division using Shakespeare. Even if we're in a Shakespeare class and someone just jumps in and then asks that question, we're like, okay, that's of a different sort of mechanism.
Yeah, that's a good analogy. Yeah.
When you first encountered ChatGPT or something more sophisticated that could answer even larger mathematical problems, did you get a sense of awe or terror initially? So I'll give you an example. There was this meeting with some other math friends of mine, and I was showing them ChatGPT when it first came out. And then one of the friends said, can you get it to explain some inequality or prove some inequality? And then it did, and then it explained it step by step. Then everyone just had their hand over their mouth like, are you serious? Really? Can you do this? And then they're like, then one friend said, this is like speaking to God. And then another friend had the thought, like, what am I even doing? What's the point of even working if this can just do my job for me? So did you ever get that sense? Like, yes, we're excited about the future and it as an assistant, but did you ever feel any sense of dread?
I'm by nature a very optimistic person. So I think it was just awe and excitement. It had always. I don't think I've ever felt that I was threatened or the community is being threatened. I could totally be wrong, but so far I just say it's like, this is such an awesome thing because it'll save me so much time looking up references and stuff like this. I can, I was happy. I was just like, wow, this is kind of cool. I mean, I guess if I were an educator, I might get a bit of a dread because there's like, undergraduate degrees, if you do an undergraduate degree, it's just basically one ChatGPT being fed to another. A lot of my colleagues started setting questions in exams with ChatGPT with fully LaTeX out equation. I mean, this is becoming the standard thing to do. I guess if you're an educator, you would probably worry. But I was thinking about just long-term discovery of, what new knowledge can we generate?
Okay.
So in that sense, this is going to be certainly an incredible help because it's got all the knowledge in the background.
Wonderful. All right, let's move forward.
Yeah, sure. So 2022 was a great year. I'm surprised this wasn't like over every single newspaper. I don't know why. At least I was told after there is some obscure outlet. I can't even remember. Some expert friends in the community told me that the ChatGPT has passed the Turing test. This is a big deal, but I don't know why it hasn't been. I was hoping to see this on BBC and every major newslet, but it didn't catch on. But anyhow, I believe that in 2022, ChatGPT has passed the Turing test. And then, where in the last two years, this is obviously where we can, this is a huge development now for large language models for mathematics. And, every major company, OpenAI, Meta AI, Epoch AI, everything, and they've been doing tremendous, work in trying to get LLM for math. Basically, you take the archive, which is a great repository for mathematics and theoretical physics, pure mathematics and theoretical physics, and then just learn that and try to generate to see it to how much. And because this is very much work in progress. And of course, AlphaGeo, AlphaGeo 2, AlphaProof, this is all the DeepMind's success. It's kind of interesting. Within a year, you've gone from 53% on Olympiad level to 84%, which is this is scary, right? Scary in the sense like impressively awesome that
right.
They could do so quickly. So basically, in 2022, an AI it's approximately equal to the 12-year-old Terence Tao. In the sense that it could do a silver medal. But of course, this is a very specialized, the AlphaGeo 2 was really just homing in on Euclidean geometry problems, which to be fair are extremely difficult, right? If you don't know how to add the right line or the right angle, you have no idea how to attack this problem. But it's kind of learned how to do this.
Yes.
So it's kind of nice. So this is all within a couple of years, and there's this very nice benchmark called Frontier Math that Epoch AI has put out. I think there was a white paper, and they got Gowers and Tao, the usual suspects, just to benchmark. Okay, fine. So you can do 84% on Math Olympiad, which is sort of high school level. What about truly advanced research problems, right? So, to my knowledge, as of the beginning of this month, it was only doing 2%. Right, so that's okay, fine. It's still not doing that great. But the beginning of this week, you learn that OpenAI 03 is doing 25%. So we've gone 20% up. We've got a fifth up within 4 weeks of what they can do. So that's wow. That's kind of very interesting.
Yeah, such a rapid improvement.
It's so this is crazy. I love this, right? Because it's exciting. It's very rare to be. I remember back in the day when I was a PhD student doing ADS CFT related algebraic geometry. Because Madhusena had just come out with a paper in 97, 98, and that's just when I began my PhD. I remember that kind of excitement, the buzz in the string community. And, people are saying, there was a paper every couple of days on the next, that kind of excitement. And I haven't felt that kind of excitement for a very long time, just because.
Wow.
And then this is like that, right? Every week there's this new benchmark, a new breakthrough. So that's why I'm finding this field of AI system mathematics to be really, really exciting.
Can you explain? Perhaps it's just too small on my screen because I have to look over here. But can you explain the graph to the left with Terence Tao?
Oh gosh, I'm not sure I can because I'm sure I can read this graph in detail. I think it's the year.
What is it trying to convey?
So it's the ranking of Terence. Oh no, this is just Terence Tao's individual performances over different years, over different
Wait,
problems.
so he's retaking the test every year?
No, he's taken it 3 times, ages 10, 11, and 12. And when he was 10, he got the bronze medal, and then he got the silver medal, then he got the gold medal within 3 years,
Okay.
at the age of 12 or something. But I can't. I think
What are those bars about?
the bar. It's a good question. I think maybe it's to the different questions. You're given 60 questions, and what it would take to get the gold medal, I think, or what it would take or to get the silver medal, I think. How many percent you have to
Okay.
correct?
Okay, so it wasn't a foolish question of mine. It's actually
No. It's a
something
good
that
question.
neither-
I have
Okay, all right.
no recollection, or maybe I never even looked at it. Or somebody told me about this graph at some point. I forgot what it is.
Okay, because it looks to me like Terrence Tao is retaking the same test, and then this is just showing his score across time, and he's only getting better. But that can't be it. Why would he
No,
retake a
that can't-
test? He's a professor.
No, I think it goes to 66. It must be like this is an open source graph.
Oh, I thought you were going to say this is an open problem in the field. What does this graph mean?
No. It's an open source. This graph is just you can take it from the Math Olympiad database.
Got it.
Which I shamelessly see again. Perfect, right? I've just done something that I have absolutely no understanding. I've presented to you like a language model, and I just copy and paste it because it's got a nice, cute picture of Terry Tao when he was little. So finally, I'll go back to the stuff that I be really be thinking about, which is this sort of top-down mathematics, right? So, and then this is kind of interesting. So the way we do research, practitioners is completely opposite to the way we write papers. I think that's important to point that out. We muck about all the time. We do all kinds. You look at my board, right? It's just filled with all kinds of stuff, and most of it is probably just wrong. And then once we got a perfectly good story, we write it backwards. And I think writing back math papers backwards, and math generally defined, math and theoretical physics papers backwards. Well, theoretical physics is a bit better. At least sometimes you write the process, but in pure math papers, everything is written in the style of Bourbaki. This very dry definition proof, and which is completely not how it's actually done at all. This is why Arnold, the great Vladimir Arnold, says Bourbaki is criminal. He actually used this word, the criminal Bourbakiization of mathematics, because it leaves out all human intuition experience. It just becomes this dry machine-like presentation,
Interesting.
which is exactly how things should not be done. But Bourbaki is extremely important because that's exactly the language that's most amenable to computers. So it's one way or another. But we, human practitioners certainly don't do this kind of stuff, right? We muck about, if we have to, and sometimes even rigor sacrifice, right? If we have to wait for proper analysis in the 19th century to come about before Newton invented calculus, we won't even know how to compute the area of an ellipse, because we have to wait and formalize all of that. You don't just go all backwards. So kind of the historical progression of mathematics is exactly opposite to the way that it's presented. I mean, it's fine, but the way it's presented is better. It's much more amenable to a proof copilot system like Lean than what we actually do.
Even science in general is like that, where we say it's the scientific method, where you first come up with a hypothesis and then you test it against the world, gather data and so on. But the way that scientists, not just in math and physics, but biologists and chemists and so on work are based on hunches and creative intuitions and conversations with colleagues and several dead ends. And then afterward, you formalize it into a paper in terms of step by step, but it was highly nonlinear. You don't even have a recollection most of the time of how it came about.
That's right. And I think one of the reasons I got so excited about all this AI for math is this direction, because this hazy idea of intuition or experience, and this is something that a neural network is actually very, very good at.
Wonderful.
It could help you. So I'm going to give concrete examples later on about how it guides humans. But just to give some classical examples, I've said this joke so many times. I think so. What's the best neural network of the 18th century? Well, it's clearly the brain of Gauss. I mean, that's a perfectly functioning, perhaps the greatest neural network of all time. And this is, I want to use this as an example because what did Gauss do? Now, Gauss plotted the number of prime numbers less than a given positive real number, just to give a sort of continuity. And he plotted this, and it's kind of a really, really, jaggedy curve, and it's a step function. It's a step function because it jumps whenever you hit a prime. But Gauss was just able to look at this when he was 16 and say, well, this is clearly x over log x. How did he even do this? Experience? I mean, he had to compute this by hand, and he did, and he got some of them wrong even. Primes. He had tables. By his time, the tables of primes were up in the tens and hundreds of thousands. He has to go up in the 100,000 range. And you can just look at this as x over log of x. And then, but this is very important because he was able to raise a conjecture before the method by which this conjecture is proved, namely complex analysis, was even conceived of by Cauchy and Riemann. And that's a very important fact. So he just kind of felt that this was x over log x. And you had to wait for 50 years before Hadamard and Delahaye-Poussin to prove this fact, because this technique, which we now take for granted, this technique called complex numbers, complex analysis, wasn't invented by Cauchy, wasn't invented yet. You had to wait for that to happen. So that's how it happens like this in mathematics all the time. Even major things. Of course, this is so. It's called the prime number theorem, which is a cornerstone of all of mathematics. Right. This is the first major result since Euclid on the distribution of primes.
Mm-hmm.
How did Gauss say this was x over log x? I don't know. Because he had a really great neural network, and this happened. It happens over and over again. Like the Besch-Swinnerton-Dai conjecture, which I'm going to talk about later, which is one of the millennium problems. And it's still open, and it's certainly one of the most important problems in mathematics of all time. And this is Birch and Swinnerton-Dai in a basement, in Cambridge in the 1960s. They just plotted ranks and conductors of related curves. I'm going to define those in more detail later. And they will say, "Oh, that's kind of interesting. The rank should be related to the conductor in some strange way." And that's now the BSD conjecture, the Birch-Swinnerton-Dai conjecture. And what they were doing was computer-aided conjectures. So here was Gauss, the eyeballs of Gauss in the 19th century, but the 20th century really have seriously computer-aided conjectures. And of course, the proof of this is still open in general. There've been lots of nice progress in this. Where we're going to go is very much what technique do we need to wait to prove something like this.
Now, is there a reason that you chose Gauss and not Euler? Like, is it just because Gauss had this example of data points and guessing a form of a function?
I'm sure Euler, who is certainly as great, had conjectures. Maybe that's an interesting point. I'll mention Euler later, but I think there's not an example as striking as this one. In fact, what's interesting, as a byproduct of Gauss inventing this, because it was kind of mucking around with statistics, right? This is before statistics existed as a field as well, right?
Yes.
This is like early 1800s. And Gauss, I think, and you can check me on this, Gauss got the idea of statistics and the Gaussian distribution because he was thinking about this problem. So it's kind of interesting. So he was laying foundations to both analytic number theory and modern statistics in one go. He was doing regression. So I think he essentially invented, regression, the curve fitting, which is our this is like 101 of modern society. He was trying to fit a curve.
Yeah.
What was the curve that really fit this? And, in the process, he got x over log x. And in addition, he got this idea of regression. Impressive guy. What can we say? He's a god to us all. And then, so the upshot of this is like I love this. Again, there's something I found on the internet, and just to emphasize, that this idea of
Speaking of God.
speaking of God, this idea of mucking about with data in pure mathematics is a very ancient thing, right? You have to this and once you formulated something like this in conjecture, you will write your paper. Imagine writing a paper. You will say conjecture, definition prime, definition pi of x, then conjecture pi of x, evidence, rather than all of the failed stuff about inventing regression and mucking about. All that stuff just gets not written at all. That intuitive creative process is not written down anywhere. So here is it's great. I'm glad I'm chatting to you about it, right? Because it's nice to have an audience with this, right? So if you look at pattern recognition, right? What do we do, right? In terms of pure mathematical data, if I gave you a sequence like this, you can immediately tell me what the next number is to some confidence. Right?
Yeah, 001.
So zeros is just this is just multiple of 3 or not. This one, I've tried this with many audiences, and after a few minutes of struggle, you can get the answer, and then this turns out to be the prime characteristic function. So what I've done here is to mark all the odd integers, and evens obviously you're going to get 0, so it's kind of pointless. So just a sequence of odd integers, and then it's a 1 if it's a prime, it's 0 if it's not. So 3, 5, 7, 8, and so on and so forth. 3, 5, 7, 9, 11, and you mark all the odd ones which are 1.
Okay.
And you can probably, after a while, you can muck about it, and you can see where this is going. The next sequence is much harder, so I'm going to give away, so we won't have to spend like a couple of hours staring at it. So this one is what's called the shifted Möbius function. What this is, just you take an integer and you take the parity of the number of prime factors it has up to multiplicity, starting from 2. I think I didn't start from 1 here. And then if it's 1, maybe I did start 1. It's 0 if it's an odd number of prime factors. It's 1 if it's an even number of prime factors for all the sequence of integers. And I hope now I've gotten this right. So it's, if I think I start with 2 has, so that's all. No, let's see, 2, 3. Yeah, so I did start with I'm going to mark 1 for 1 just to start this, kick off the sequence. And then 2 is a prime number. It has only 1 prime factor. It's an odd number. 3 is an odd number of prime factors. 4 is 2 because it's 2 squared. So it has an even number of prime factors, and so on and so forth. So 5 is prime. It has 1 odd number. 6 is 2 times 3. So it has 2, an even number of prime factors, and so on and so forth.
Mm-hmm.
So it looks kind of harmless. What's really interesting, so this is even number. So if you stare at this for a while, it's very, very hard to recognize a pattern. And what's really interesting is that to know the parity of the next number, if you have an algorithm that can tell me the parity of this in an efficient way, you will have an equivalent formulation of the Riemann hypothesis. So that's actually an extremely hard sequence to predict. So if you can tell me with some confidence more than 50% what the next number is, without looking up some table, then you can probably end up cracking every bank in the world.
Interesting.
Because this is equivalent to the Riemann hypothesis. So I'm just giving 3. So trivial, kind of okay-ish, really, really, really hard.
Yes.
So now you can think about a question. How, if I were to feed sequences like this into some neural network, how would a neural network do? So one way to do it, so this goes a bend. So we go way back to the very beginning, to the question of what is mathematics. And, Hardy, in his beautiful apology, says, what mathematicians do is essentially we are pattern recognizers. That's probably the best definition of what mathematics is, or is that it's a study of patterns, finding regularity in patterns. And in fact, if there's one thing that AI can do better than us, is pattern detection, because we evolved in being able to detect patterns in 3 dimensions and no more. So in this sense, if you have the right representation of data, you're sure that AI can do better than that. I mean, generate a lot of stuff, but filtering out what is better is a very interesting problem in and of itself. So let's try to do one. I mean, there are various ways to do this representation. One way you can do it is to do a problem which is maybe best fit for an AI system, which is binary classification of binary vectors. So what you do is, sequence prediction is kind of difficult. So one thing you can do is just take this infinite sequence and just take, say, a window of 100, 1,000, fixed window size, and then label it with the one immediately outside the window, and then shift, label. So then you can generate a lot of training data this way. So for this sequence, I think I've just taken here, whatever the sequence is, and I might just with a fixed window size and with this label. So now you have a perfectly supervised, perfectly defined binary supervised machine learning problem. Then you pass it to your standard AI, algorithm that they're just out of the box ones. Nothing. You don't even have to tune your particular architecture. Just take your favorite one, and then do cross validation. The standard stuff. Take sample, do the training, and then try to validate this on unseen data. So if you do this to the Moth 3 problem, to this one, you immediately find that any neural network or whatever Bayes classifies would do it 100% accuracy, as it should, because you'll be really dumb if it didn't, because this is just a linear transformation. So even if you have a single neuron that's just doing linear transform, that's good enough to do it.
Mm-hmm.
The prime Q problem, I did some experiment, like 7 years ago, and it got 80% accuracy. And I was like, wow, this was a wow moment. I was like, why is it doing 80? I don't have a good answer to this. Why is it doing 80% accuracy to this? But how is it learning? Maybe it's doing some sieve method, which is kind of interesting. The second number is just to chi-square, just to double test that the what's called MCC, which is Matthews correlation coefficient. These are just buzzwords in stats. I never learned stats, but now I'm relearning. I took Coursera in 2017, so I can relearn all these buzzwords.
Great.
It's great. It's really useful. And then this shifted Liouville lambda function. It's sorry, I think I made I mistakenly called this Möbius mu function. It's not. I mean, it's related, but it's not. It's the shifted Liouville lambda function.
Got it.
Sorry, one of my neurons died when I said Möbius mu, but it's Liouville lambda.
You were subject to the 1 pixel attack.
Yeah, but so this one I couldn't break 50%. Right, 0.5 just means it's coin toss. It's not doing any better guessing than whatever. And this chi-square is 0.00. That means I'm up to statistic error. So which means I couldn't find an AI system which could break, which could do better than random guess. I'm not saying there isn't one. It would be great if there were one. And then so it's kind of it's life. And I couldn't. If I do break it, I might actually stand a good chance breaking every bank in the world.
All right,
but I haven't made it worse.
Let's remain close friends.
Yeah, that's right. So I was very proud of this, because this experiment, I'm going to mention a bit later. This Liouville lambda was just thing I was just trying, like way back when. But apparently, Peter Sarnak, whom I really admire, he's one of the world's greatest number theorists, current number theorist, and I got to know him through this memorization thing that I'm going to talk about later, and I reminded him that I almost became his undergraduate research student. I ended up doing I was an undergrad at Princeton where I had a 2 path I could follow. For it kind of defines your undergraduate thesis, right? So
yes.
One was in mathematical physics, one was that's with Alexander Migdal, and the other one was with two problems, and the other one was actually offered by Peter Sarnak on arithmetic problems. And I somehow because I wanted to understand the nature of space and time, I went through the Alexander Migdal path to do mathematical physics, which led to do string theory. And I come after 20, 30 years, I came full back to be in Peter Sarnak world again. I met him at this conference. I reminded him of this, and he was very happy. But also, actually, what's really interesting is that he was asking DeepMind the same question a few years ago about the Deluvio Lambda, whether DeepMind could do better than 50%. So I was glad that I thought along the similar lines as a great expert in number theory, and somebody who could have potentially have been my supervisor, and then I would have gone into number theory instead of string theory, which is whatever. It's how life happens.
So perhaps you're going to get to this later on in the talk, but I notice here you have the word classifier, and the recent buzz since 2020 or so has been with architecture, the transformer architecture in specific. So is there anything regarding mathematics, not just LLMs, that has to do with transformer architecture that's going to come up in your talk?
Not specifically. It's interesting. I'm one of my colleagues here at the London Institute. He's Mikhail Burtsev. He's an he's our institute's AI fellow, and he's an expert on transformer architecture. So I've been talking to him, and we're trying to get to devise a nice transformer architecture to address problems in finite group theory. It's in the works. So, but nothing so far is, even with the memorization stuff, is very basic neural networks that we didn't use anything more sophisticated than that. So to be determined whether it will outperform these standard ones will be kind of interesting.
Got it.
Yeah. So actually, now we go way back to the beginning of our conversation. Is how I got into this stuff, and that I don't know. Completely coincidentally was through string theory. So at this point, maybe I just give a bit of a background of, how all this stuff came about.
Please.
That if, at least personally, why was I even thinking about this? Because I knew nothing about AI, 7-8 years ago. Zero, literally zero.
Yes.
I knew nothing more than to read it on the news, from the news. And this is actually a very interesting story, which shows again the kind of ideas that the string theory community is capable of generating. Just because you got all these experts looking on kind of interesting problems. So let's go way back. And again, I've quoted Gauss, right? I have to say something about Euler. So this is a problem. Again, this is you can see I'm very influenced by 3. The number 3. I'm a total numerologist, right? Trinity, name the 3. 3 is something, right? And then there is called the trichotomy classification theorem by Euler. This dates to 1736. So if you look at, so I'm going to say the buzzword, which is connected, compact, orientable surfaces. Right, so these are, the words explain themselves. They have no boundaries.
Yes,
and they're, topologically, whatever the topological surfaces. Right? So Euler was able to realize that a single integer characterizes all such surfaces. So this is the standard thing that people see in topology, right? So the surface of a ball is the surface of a ball, and you can deform it. The surface of a football is the same as an American football. You can deform without cutting or tearing. And then the surface of a donut is the same as your cup. Right, because it's everything that everyone, the standard thing. It has one handle, and then so the surface of a donut is exactly the topologically what they call topologically homomorphic to the cup, and then you got the pretzel. So I think that's a pretzel, or maybe I think this is like the German pretzel, and it gets more and more complicated. But Euler's because Euler invented the field of topology. So he realized this idea of topological equivalence in the sense that there's a single topological invariant which we now call the Euler number, which characterizes these things. An equivalent way to say is the genus of these surfaces is, no handles, one handle, two handle, three handles, and so on and so forth. It turns out that the Euler number, what we now call the Euler number, is 2 minus twice the genus. So 2 minus 2g. Okay, that's great. So that's the classic Euler's theorem. And then, comes in Gauss, right? Once you got these three names next to each other, Euler, Gauss, and Riemann, it's got to be some serious theorem, right? So Euler did this in topology, and then Gauss did this incredible work, which he himself calls him the Theorema Egregium, the great theorem, which he considers this is his personal favorite, and this is Gauss, right? And Gauss said you can relate this number to which is, this number is purely topological. You can relate this number to metric geometry. So he came up with this concept, which we now call Gaussian curvature. It's just some complicated stuff. You can characterize this a curvature, which you can define on this. Well, this is even before the word manifold existed, right? On the surface, and then you can integrate using calculus, and the integral of this Gaussian curvature divided by 4 pi is exactly equal to this topological number. And that's incredible, right? The fact that you can do an integral, it comes out to be an integer, and that integer is exactly topology. So this idea, this Gauss-related geometry to topology in this one sweep. And then what's even the next level comes Riemann. Riemann says, well, what you can do is to complexify. So these are no longer, real connected, compact, orientable surfaces, but you can think about these as complex objects. So what do we mean by that is, well, if you think about, the real Cartesian plane, that's a two-dimensional object, but you can equally think of that as a one complex dimensional object, namely the complex plane.
Or the complex line.
Yeah, the complex line, exactly. So what's R2, Riemann would call C. And then Riemann realized that you can put similar structure on all of these things as well. So all of a sudden, these things are no longer two-dimensional real orientable surfaces, but one complex dimensional it's now called curves. It's a terrible name. So a complex curve is actually a two real dimensional surface. And it turns out that all complex curves are orientable. So you already rule out things like Klein bottles and stuff like that, or Möbius strips.
Yeah.
So the complex structure requires orientability, and that's partly because of Cauchy-Riemann relations. It puts a direction. You can't get away. But the idea is that the interesting thing is all of these now should be thought of as one complex dimensional curves. They're called curves because they're one complex dimension, but they're not curves, right? They're surfaces in the real sense, right?
Yes.
So now here comes. So if you apply this to the Gauss thing, you get this amazing trichotomy theorem, and the theorem says, if you do this to the curvature, you can see this. The number here is 2. Right, you get the Euler number 2, which is a positive curvature thing, right? And that's consistent with the fact that the sphere is a positively curved object. Locally, everywhere, it has positive curvature. If you do it to a torus or the surface of a donut, which is just called the algebraic donut, you integrate that, you get zero curvature. And this is not a surprise because you have a sheet of paper. You fold it once, you get a cylinder, and you fold it again, you glue it again, you get this torus, this donut. And this sheet of paper is inherently flat.
Yes.
Right. So if you just take a piece of paper, you roll. You take this piece of paper and you roll it up, you get a cylinder, and then you do it again. I'm not gonna. You get the surface of a donut, like a rubber tire, and that is inherently zero. It's zero curvature, and then you can do this, and this is a consequence of what's known as Riemann uniformization theorem. If you do anything that has more than one handle, you get zero curvature. So now you have the trichotomy, right? You have positive curvature, zero curvature, and negative curvature. The one in the middle is really, obviously, it's interesting. It's the boundary case. In complex algebraic geometry, these things are called Fano varieties.
Earlier you said if you have anything that's more than one handle, you have zero curvature. You meant negative curvature.
Oh, sorry, I meant negative curvature. Negative,
Okay.
yeah.
So these fidget spinners on the right, they all have negative curvature.
Everything here has negative curvature.
Got it.
So now in the world of complex algebraic geometry, these positive curvature things are called Fano varieties, after this Italian guy Fano. These negative curvature objects which proliferate are called varieties of general type. And this boundary case are called zero curvature objects. And it just so happens we now call things in the middle Calabi-Yau, these zero curvature objects.
Yes.
So far, this got nothing to do with physics. I mean, it's just the fact of topology, right? But this is such a beautiful diagram that took from 1736 until Riemann. Riemann died in the 1860s, I think, or something like that. So it took 120 years to really formulate just this table to relate metric geometry to topology to algebraic geometry. It's kind of a beautiful thing, right? So to generalize this table is the central piece of what's now called the minimal model program in algebraic geometry, for which there have been all these Fields medalists, Pierre Carr a couple of years ago, and then it started with Mori, who got the Fields medal, and then this whole Mukai and this whole distinguished idea. So basically this minimal model program is to just generalize this to higher dimension. This is complex dimension 1, right? How do you do it? It's very hard. And once you have it, I won't bore you with the details. This is very nice. There's topology, algebraic geometry, differential geometry, index theorem. They all get unified in this very beautiful way. And you want to generalize this to arbitrary dimension, arbitrary complex dimension. It'd be nice. And it's still an open problem. How do you do it in general? It's a very nice problem. But at least for a class of complex manifold known as Kähler manifolds, I won't bore you with the details, but Kähler manifolds where the metric has very nice behavior. There's a potential for which you can have a double derivative that gets on the metric. And then it was conjectured by Calabi in the 50s. Again, 54, 56, 57. It was a great year, right? That's all these different ideas. I mean, in 3 completely different worlds now come together because mathematical physicists have kind of tied it up, the world of neural networks, the world of Calabi conjecture, the world of string theory to one. I like, when things get bridged up in this way, But, again, the theorem itself is extremely technical. But the idea is, for these Kähler manifolds, there is an analog of this diagram, basically.
I love this slide. I saved this slide for my own private notes.
Okay.
I keep a collection of dictionaries in physics and math.
Yeah.
I think this is beautiful.
Yeah, me too. I mean, but it took me years to do this table because it's not written down anywhere. And it touches different things. I think it's not written down anywhere precisely because math textbooks are written in the Bourbaki style. But now it just becomes clear what people have been thinking about for the past 100 years. After Grothendieck, it's just trying to relay these ideas. This is intersection theory of characteristic classes.
Yes.
So this is topology, and this is over 200 years of work of the central part of mathematics.
And mathematicians like Chern, Ricci, Euler,
everybody was ever involved in this diagram is an absolute legend. In fact, there is one more column to this diagram. I think for sure. I think when I did this was a slide from some time ago. But when I was talking to a string audience, there is one more, which is relations to L function, and that's when number theory comes in. So there is one more column. And to understand this world, to this one more column of its behavior to L functions, that's the Langlands program.
Right.
So it's actually really magical that this table actually extends more. As far as, I mean, that's just as far as we know now, right?
Of
The L
course.
functions and its relations to modularity. And I think this is, of course, obviously mathematics. To me, like, mathematics is about extending this table as much as possible to let it go into different fields of mathematics. So, but at least for sure, we know there is one because of the Langlands correspondence. There is one more column, and that column should be on number theory and modularity.
And soon there'll be another table on the Yang invariant, the He invariant.
No, I don't think I have enough talent to create something that. But it could well be there should be something new to new.
Right.
But that's to me, that's really the most fun part about mathematics. It's not so. I mean, there, like, I who was it? I think maybe it's Arnold as well, who says, there are two types of mathematicians. There are the hedgehogs and there are the birds. Right, hedgehogs really
Specialize.
specialize. I mean, you absolutely need it. I think who is a great hedgehog. I think Zhang, the guy who made this first major breakthrough in the prime gap. I mean, he's been spending his entire life just trying to think about can I bound the how many what's the lim sup of the distance between prime pairs, and the technique he uses is beautifully argued analytic number theory technique, Sieve methods, kind of the Ben Green world of Sieves and James Maynard. And then there are the birds who are like, I'm just going to just fly around. I may bump into trees and whatnot, but I'm just trying to see whether they can do. And people like Robert Langlands, and they're very much in that world. Can I see from a distance? I may get very coarse grained view.
And which are you?
I'm 100% in the bird category. I mean, what I like to go, once I see something, and I of course sooner or later you need to dig like a hedgehog, but the most thrill that I get is when I say, oh wow, this gets connected.
So the results are proven when you dig, but the connections are seen when you get the overview.
Yeah, absolutely. So I mean, of course, again, this is a division that's kind of artificial. All of us we do a bit of both.
Yes.
The guy who really does it well is I forget to mention. Of course, it's become like a grand. Well, he passed away. This John Mackay, who is a Canadian, probably the greatest Canadian mathematician since Coxeter. John Mackay really saw unbelievable connections in fields that nobody will ever see. And he passed away. He became sort of, in the last 10 years of life, he became sort of like a grandfather to me. He saw my kids grow up, over Zoom. So the London Math Society asked me to write obituary. I was very touched by this, and so I wrote his obituary for it. And I was just trying to say, well, this guy is the ultimate pattern, linker. So John Mackay, absolute legend.
Great.
Moving on. I mean, this is very much a huge digression for what I'm actually going to tell you about, which is the Birch test for AI, and that's
great.
Do you have a limit on what these videos are?
No, just so you know, some of them are 1 hour, some of them are 4 hours, and people listen for all of it.
Yeah, this is great fun.
Great, yeah, same. I'm loving this.
Yeah, me too. Because normally, I have 1 hour, 55-minute cutoff. I could give a talk, right? Then in like 5 minutes questions. And they're like, oh my God, I haven't said most of the stuff I wanted to say.
Yeah, exactly. Because the point of this channel is to give whoever I'm speaking to enough time to get through all of their points, rather than they're rushing and not covering something in depth. I want them to be technical and rigorous. So please continue.
Sure. Sounds good to me. So in that magical year of 1957 of neural networks, the magical year of what else? The automated theorem prover world and the world of algebraic geometry, in three different worlds. They didn't even know of each other's names, let alone the results. Calabi conjectured that, at least for Kähler manifolds, this diagram is very much well defined, this table. And Yao proved it 20 years later. So Shintun Yao, who is very, is again very much like a mentor to me, and he gets the Fields Medal immediately. Right, so you can see why this is so important. He gets the Fields Medal because this idea of falling through Calabi is trying to generalize this sequence of ideas of Euler, Riemann, and Euler, Gauss, and Riemann. So it's certainly very important. So there it is. We can park this idea. So Yao showed that there are these Kähler manifolds that have this property, that have the right metrical properties. So by metric, I mean distance. Something you can integrate over. That because here you never think that this integral is messy, right? Even if you do this on a sphere, right? This R has all these cosines and sines that have got they've all got to cancel at the end of the day to give 4 pi.
Yes.
Like what the hell? And then divided by 2 pi, you get 2, and that's the Euler number, which is kind of amazing stuff. And now you can do this in general. Just as a caveat, Yao showed that this metric exists. He never actually gave you a metric. So the only currently known metric on these things is for the zero curvature case, it's just the torus. Anything above that, we don't know. We just know that it exists. And if you did this integral, you're going to get like 2, 5, or whatever the number is, which is kind of amazing. This is like a completely non-constructive proof.
What's interesting is that these automated theorem provers, they seem computational. And it's my understanding that computationalists, so people who use intuitionist logic, they don't like constructive proofs. Sorry, they like constructive proofs. They don't like non-constructive proofs. Right. In other words, existence proofs without showing the specific construction.
Right.
So it's interesting to me that all of undergraduate math, which has some non-constructive proofs, are included in Lean. So I don't know the relationship between Lean and non-constructive proofs, but that's an aside.
Right, that's an aside. I probably won't have too much to say about it. Cool. So back to I don't know why I went on this diatribe on digression on string theory, but I just want to say that this is a side comment. So this is something since 1736, which is kind of nice. Which is Oh, by the way, that's actually kind of interesting. I'm going to have to check this again. Just down the street from the institute is the famous department store Fortman Mason's, which I think is established in 17 something. It's a great department store. It's not where I usually do my shopping, but it's just a beautiful department store where, Mozart would have, and Haydn might have, come and did their, Christmas shopping. But anyhow, just random thought. So string theory was just one slide, right? I mean, I'm not, in some sense, I'm not a string theorist in the sense, I don't go quantize strings. The kind of stuff that I'm more interested in is like, I didn't grow up writing conformal field theories and do all that stuff. It's just that for me, it's an input, so I can play with a little more problems in geometry.
Yeah.
So string theory is this theory of space-time that unifies quantum gravity, blah, blah, blah. And then it works in 10 dimensions, and we've got to get down to 4 dimensions. So we're missing 6 dimensions. So that's what I'm going to say. And this amazing paper in 1985 by Candelas, Horowitz, Strominger, and Witten, they were thinking about what are the properties of the six extra dimensions. So what is interesting is that by imposing supersymmetry, and this is why supersymmetry is so interesting to me, by imposing supersymmetry and other, anomaly cancellation, bunch of not too stringent conditions, they hit on the condition that this 6 extra dimensions has to be Ricci flat. Ricci flat is, you can understand, because it's vacuum Einstein solutions. It's, you want the vacuum string solution. And then a condition which you've never seen before, which just happens to be this Kähler condition. They didn't know about this. No physicist until 1985 would know what a Kähler manifold was. And it's complex, and it's complex dimension 3. Remember, again, I said complex dimension 3 means real dimension 6, right? That's 10 minus 3 is 6, 10 minus 4 is 6, and 6 needs to be complexified into 3. And again, this is just an amazing fact that in 1985, Strominger, who was a physicist, was visiting Yao at the Institute of Advanced Study in Princeton. And so he went to Yao and said, "Can you tell me what this strange condition, this technical condition I got?" And Yao says, "Wow, I just got the Fields Medal for this. I think I may know a few things." It's just amazing. It was a complete confluence of ideas that's totally random. And the rest is history. So in fact, these four guys named this Ricci-flat Kähler manifold Calabi-Yau. So it wasn't the mathematicians who did it. This word Calabi-Yau came from physicists, so from string theorists, which now, of course, Calabi-Yau is now one of the central pieces. And so this is so Philip Candelas was my mentor at Oxford, and when I was a junior fellow there, and he tells me this story. He's a very lively guy. He tells me about how this whole story came about, and it's very interesting. And but so he and these four guys came up with the word Calabi-Yau. So all of a sudden we now have a name for this boundary case in complex algebraic geometry. This bounding case is now known as a Calabi. So remember we had names before, right? This was the Fano variety. This was varieties of general type, and this bounding case is now called Calabi-Yau.
So what we're seeing with the torus here is a Calabi-Yau 1.
Exactly. So exactly. In fact, the torus is the only Calabi-Yau 1. So it's the only one that's Ricci-flat. I mean, by this classification, it's the only one that's topologically possible. So that's kind of interesting, right? And then this is just a comment. I like this title because I think your series is called TOE. This is a TOE on TOE.
Love it.
I just want to emphasize this is a nice confluence of ideas with mathematical physics. But with string theory, really, what it really is this brainchild of interpreting problems interpreting and interpolating between problems in mathematics and physics. Right. So, for example, we now GR should be phrased in differential geometry. The standard model gauge theory should be phrased in terms of algebraic geometry and representation theory of finite groups. And condensed matter physics of topological insulators should be phrased in terms of algebraic topology. This idea, I think the greatest achievement of the 20th century physics is, to me, and I think something you would appreciate since you like tables.
Yes.
So here's a dictionary of a list of things, and then here's what they are in mathematics. And then, you can talk to mathematicians in this language, and you can talk to physicists in language, but they're actually the really same thing. What's a fermion? It's a spin representation of the Lorentz group. That I like that because it gives a precise definition of what we are seeing around. Then you have something you can purely play with in this Platonic world. And string theory is really just the brainchild of this translation, this tradition of what's on the left and what's on the right, and let's see what we can do. And sometimes you make progress on the left, you give insight on stuff on the right, and sometimes you make progress on the right and you give insight on the left.
Why is it that you call the standard model algebraic geometry? Because bundles and connections are part of differential geometry, no?
Oh yeah, that's true. Well, I think that's they're interlinked, and I think algebraic. Maybe it's because of Atiyah and Hitchin. Of course, they are fluid in both. They go so. I mean, they go either way, but algebraic in the sense that you can think of you can often work with bundles and connections without actually doing the integral in differential geometry. So I think that's the part I want to emphasize. You can understand bundles purely as algebraic objects without ever doing an integral. Like here. Like here, for example, like this integral is obviously something you would do in differential geometry. But this integral, the fact that it comes to be an integer, was explained through the theory of Chern classes to be this integral is a pairing between the Chern class, between homology and cohomology, which is a purely algebraic thing. We all try to avoid doing integrals because integrals are horrible because it's hard to do. And in this language, it really just becomes polynomial manipulation, and it becomes much simpler.
Okay.
So that in that sense, I want to put. Of course, it's a bit of a both.
Got it.
So I like doing this diagram, right? And if you look at the time lag between the mathematical idea and the physical realization of that idea, I mean, there really is a confluence.
Yeah.
It's getting closer. I mean, these things going up and down. I mean, I'm just saying in the past, if you take the last 200 years, or last 100 years or so, of the groundbreaking ideas in physics, there is this.
Interesting.
Right. It gets shorter and shorter. So, I mean, obviously Einstein took ideas of Riemann, and there was a 6-year gap. Dirac was able to come up with the equation of the electron, essentially because of Clifford algebras.
Historically, was he motivated by Clifford algebras, or was it later realized, hey, Dirac, what you're doing is an example of a Clifford algebra?
So I believe the story goes, in order to write down the first time derivative version of the Klein-Gordon equation, which is a second order, that's the bosonic one, he had to do some essentially he factorized the matrix in a way that seemed very strange to him. And Dirac said, this really reminded me of something that I've seen before. And this is one of these moments, right? Today, we can chat GPT this.
Mm-hmm.
But what Dirac did was, he said, he was at St. John's in Cambridge at the time. He said, I have seen this in a textbook before somewhere, this gamma nu thing. And then he said, I need to go to the library to check this. So he really knew about this. And unfortunately, the St. John's library was closed that evening. So he waited until the morning, until the library was open, to go to Clifford's book, or a book about Clifford. I can't remember whether it was Clifford's book or maybe it was one of these books. And then he opened up, and he really knew, and that this gamma nu anti-commutation relation really was through. And so he knew about Clifford.
Cool.
It's kind of interesting. Yeah. Just like Einstein knew about Riemann's work on curvature. But whether you could say, Dirac was really inspired by Clifford, he certainly did a funky factorization, and then he knew how to justify it immediately by looking at the right source. And then similarly, Yang-Mills theory depended on this Zeibert's book on topology. And then, by the time you get to Witten and Borcherds, really there's this. This diagram for me is like what gets me excited about string theory.
Mm-hmm.
Because string theory is a brainchild of this curve, this orange curve. And now it's getting mixed up. I mean, of course, people hear about this great quote that Witten says, string theory is a piece of 21st century mathematics that happens to fall into the 20th century. And I think he means this.
Yes.
That he was using supersymmetry to prove, theorems in Morse theory, and vice versa. Richard Borcherds was using vertex algebras, which is sort of foundational thing in conformal field theory, to prove some properties about the monster group. We're at this stage, and of course, this was turn of the century, and now we're here, and we have to. Where are we now? Are we crisscrossed, or are we parallel?
Yeah,
it's hard to say.
And in a meta manner, you can even interpret this as the pair of pants in string theory with the world sheet.
Yeah, cute, very cute. Yeah, why not? Yeah, it is. But going back to what you were saying, how I got to. Oh yeah, so just this confluence idea. Of course, everyone quotes these two papers. When Wigner was thinking about in 1959, why mathematics is so effective in physics, and there's this maybe slightly less known paper, but certainly equally important paper by the great late Latia, and then Dijkgraaf and Witten, Dijkgraaf and Hitchen, which is the other way around. Why is mathematics so why is physics so effective in giving ideas in mathematics? So this is a beautiful pair of essays. In this is like very much in the world of a summary of the kind of physics ideas from string theory is making such beautiful advances in geometry. So this is a very beautiful pair of one given in the other that needs to be sort of praised more. And that's why you were mentioning earlier how I got to know Roger so well is through these editorials. We try to collect with my colleague Mo Linke, who is a former director of the Chern Institute. So everybody's connected, right? So it just so happens that I grew up in the West, but with my parents after so many decades, my parents actually retired and went back to Tianjin, where Nankai University is, where Chern founded what's now called the Chern Institute for Mathematical Sciences. And that's an institute devoted to the dialogue between mathematics and physics. In fact, 1/3 of Chern's ashes is buried outside of the Math Institute. There's a great, beautiful marble tomb.
Interesting.
And 1/3 not because of any mathematical reason. It's just that he considered 3 parts of his home. So his hometown in Zhejiang, China, and Berkeley, where he did most of his professional career, and then Nankai University, where he retired to for the last 20 years of his life. So 1/3 each.
Yes. The number 3 comes up again. That numerology.
There we go. It's all about 3. And in fact, I was going to joke. So in Chern-Simons theory in 3 dimensions, there's this topological theory, in Chern-Simons theory. There's a crucial factor of 1/3. I always joke, that's why Chern chose 1/3 for his ashes, but that's it's complete coincidence. But it's actually what is actually interesting is that tomb, that beautiful black marble tomb. For somebody as great as Chern, it mentions nothing about he achieved done this, done the other thing. It's just 1 page of his notebook. I mean, think about the poor guy who had to chisel all that. He have no idea what he's chiseling, right? The guy who's chiseling this thing, and it's the proof of this. The fact. Essentially, and of course, it's a little. You can look this on the internet. Just say the grave of SS Chern at Nankai University.
Well, the whole conversation we've had is just about pattern matching without the intuitive understanding behind it. So this chiseler may have had that.
Yes. That's what I do every day. I love it. So that chisel is essentially his proof why this is equal to this. Why this intersection product is the same as this integral. So he essentially it's where the Gauss-Bonnet theorem is a corollary of this trick in algebraic geometry, which is his great achievement. But anyhow, so back to this coincidence, and it just so happens that my parents, after drifting all these years in abroad, they retired back to Tianjin, where the Chern Institute is. So that's why it became an honorary professor at Nankai, because my motivation was purely just so that I could spend time to hang out with my parents. But it just so happens that it happens to be there, and then I can just pay my homage to Chern and just to see his grave. I mean, it's a great, it's a mind-blowing experience just to see the Chern's grave and to see the derivation of this in his handwriting chiseled in stone. But anyway, so that's how I got involved with Xian Yang, because he was very deeply involved with Chern. He and Chern are good friends. I can imagine that Xian Yang is 102 today.
Yeah, it's remarkable.
And that he was still doing. He wrote the preface to this when he was 99. These guys are unstoppable. And Roger Penrose sent his essay to this one when he was 92. Yeah, these guys. Anyhow, it's kind of you like tables, right? I love tables. So the tables here's just like where just a speculation of where string theory is going. Here's a list of the annual conferences. The series where string theory has been happening. So 1986 was the first string revolution, where since then every year there's been a major string conference. I'm going to the first one I'm going to for years in 2 weeks' time. It happens to be Abu Dhabi. I get some sun. And then, there's serious one like string. There's a series of annual ones, the string pheno, and then string math came in as late as in 2011. That's kind of interesting. So that's like, 30 years after the first string conference, and the various other ones. What's really interesting one is in 2017 is there's the first string data. This is when AI entered string theory. And so it's kind of so what I read the first paper in 2017 about AI assisted stuff, and there were 3 other groups independently mining different AI aspects and how to apply to string theory. So that the reason what I want to mention is just why was with the string community even thinking about this problems in AI.
Oh, and also just to be clear, briefly speaking, I'm not a fan of tables per se. I'm a fan of dictionaries because they're like Rosetta Stones. So I'm a fan of Rosetta Stones and translating between different languages. So you mentioned the siloing earlier. Sure. And mathematicians even physicists call them dictionaries, but technically they're thesauruses. Like a dictionary, you just have a term and then you define it. The translations.
Right, yeah. Like Rosetta Stones.
Yes, yeah.
No, absolutely. I guess that's why you like Langlands so much.
Yeah.
Yeah, for sure. Yeah, absolutely.
In some way, this whole channel is a project of a Rosetta Stone between the different fields of math and physics and philosophy.
Right. Yeah, that's fantastic. Love it. Big fan.
Thank you. Okay, so do you want to I noticed it jumped back to number 13. So it seems like I thought we were at 39 out of 40 or 37.
No, because I've learned this nonlinear structure. It's like, because you see, like I've learned this is really dangerous. I've learned like the click button in PDF presentations. Like you click it jumps to another one, and you can have interludes. So it's clearly an interlude. And you say you jump back to your main.
Okay.
So my actual main presentation is only like 30 pages, but it's got all these digressions, which is actually very typical of my personality. So I gave you this big interlude about string theory and Clabeyard manifolds, right? So now we've already got to the point that Clabeyard one-fold, the one-dimensional complex Clabeyard fold, there's only one example. That's just one of these. Right, and then it turns out that in complex dimension 2, there are 2 of these. There is the 4-dimensional torus, and then it's this crazy thing called the K3, which is Ricci, Flatt, and Kähler. So you got 1 in complex dimension 1, 2 in complex dimension 3. You would think in 3 dimensions, there's 3 of these things that are topologically distinct. And unfortunately, this is one of the sequences in mathematics that goes as 1, 2, we have absolutely no idea. And we know at least 1 billion. At least. So it's kind of, it goes 1 to a billion. And so Clabeyard, so starting from complex dimension 3 just goes crazy. It's still a conjecture of Yau that in every dimension, this number is finite. So remember this positive curvature thing, this funnel thing to the very top. It is a theorem that in every dimension, funnel varieties is finite in possibility in topology. That only a finite number of these that are distinct topologically. It's also known that the negative curvatures is infinite in every dimension. And when it goes higher, it's like even uncountably infinite.
Oh, interesting.
But is this boundary case, Yau conjectures, in an ideal world, they're also finite. But we don't know. This is the only open conjecture.
Now, the billion, are any of them constructed? Or is it just the existence?
Yeah. So now that's exactly where we're getting. So
Got it.
It's gotten, it's 1, 2, and 3. 3 is like, how are you going to list these things, right? And then algebraic geometers never really bother listing all of them out. This is just not something they do. So the physicists took on the challenge. So Philip Candelas in France, and then Harold Schkake and Maximilian Kreutzer started just listing these. And that's why we have these billions. There is actually databases of these. And they're presented in, just like matrices like this. I won't bore you with the details of these matrices. These are algebraic varieties. You can define these as, like intersections of polynomials. That's one way to present them. And in Kreutzer and Schkake's database, they put in vertices of toric varieties, how to embed. But the upshot is that, there's a database of gigas, of many, many gigabytes that really got done by the certainly by the turn of the century, by year 2000. These guys were running on Pentium machines. I mean, this is an absolute feat, especially Kreutzer and Skarke. They were able to get 500 million of these things stored on a hard drive using a Pentium machine of this Calabi-Yau manifold. And they were able to compute topological invariance of these. So I happen to have this database. I could access them, and that was kind of fun. And I've been playing on and off with them for a number of years. So, and a typical calculation is like, you have something like a configuration of tensors of, here is even in integers. And you have some standard method in algebraic geometry to compute topological invariance. And this topological invariance, again, in this dictionary means something. So, for example, H21 in some context is the number of generations of fermions in the low energy world. So that's a complete problem in this computing a topological invariant in algebraic geometry. And there are methods to do it. And in these databases, people took 10, 20 years to compile this database, and we got these things in. And they're not easy. It's very complicated to compute these things. So in 2017, I was playing around with this. And the reason is why I was playing around with this was very simple. It's because my son was born, and I had infinite sleepless nights that I couldn't do anything, right? I had there's the kid. And then,
there's the kid.
There's the kid. And, and he wakes you up at 2, put him to, and I was bottle feeding him. And I had a daughter at the time. So my wife's taking care of the daughter. They're passed out. And then I got this kid, I passed him out, put them into bed. And I'm wide awake at this point. It's like 2 a.m. It's like I can't fall asleep anymore. And I can't do real, serious computation anymore because I'm just too tired. So let's just play around with data. At least I can let the computer help me to do something. And then that's when I learned, well, what's this thing that everybody's talking about? Well, it's machine learning.
Right.
So that's why I got through this. It's a very simple biological reason why I was trying to learn machine learning. So then I think I was hallucinating at some point, right? I was like, well,
okay.
If you look at pictures like, matrices a lot, like, we're talking about, 500 million of these things, right?
Yes.
I wasn't going through all of them. And they're being labeled by topological invariance. How different is it if I just sort of pixelated one of these and labeled them by this? And all of a sudden, this began to look like a problem in hand-digit recognition, right? This is like, how different is this, or image recognition? So, and I just literally started feeding in. I took 500 million is too much, right? So I took like 5,000 of these, 10,000 of these, and then trained them to recognize this some number. And I was like, this is going to be like, it's just going to give crap. Obviously, it's going to give 0% accuracy. And to my surprise, it was giving extremely good accuracies. So somehow the neural network that I was training, I was even using standard MNIST, the hand recognition, MNIST things, recognizing this. And it was recognizing it to great accuracy. And now, people have improved this, like loads of people, like, Finatello, there's a group there that did some serious work on just trying to this problem. But this idea suddenly didn't seem so crazy anymore. The idea seemed completely crazy to me because I was hallucinating at 2 a.m. and it was so. But what's the upshot of this? The upshot is somehow the neural network was doing algebraic geometry, like this kind of algebraic geometry. Really sequence chasing, very complicated Bourbaki style stuff without knowing anything about algebraic geometry. It somehow was just doing pattern recognition, and somehow it's beating us. Because, if you do this computation seriously, it's double exponential complexity. But it's just now, but pattern recognition is bypassing all of that. So then I became a fanatic, right? Then I said, well, all of algebraic geometry is image processing. And so far, I have not been shot by the algebraic geometers, because it's actually true. If you really think about it, any algebraic, the point of algebraic geometry, the reason I like algebraic more than differential is because there's a very nice way to represent manifolds in this way. Manifolds in algebraic geometry. So in differential geometry, manifolds are defined in terms of Euclidean patches. Then you do, transition functions, which are differentiable, C infinity, blah, blah, blah. But in algebraic geometry, they're just vanishing loci polynomials.
Mm-hmm.
And then so once you have systems of polynomials, you have a very good representation. So for example, here, I'm just recording the list of polynomials, the degrees of polynomials that are embedded in some space. And that really is algebraic geometry. So basically any algebraic variety, so that's a fancy way of saying this polynomial representation of a manifold, which is called an algebraic variety, this thing is representable as in terms of a matrix or a tensor, sometimes even an integer tensor. And then the computation of invariance, or topological invariance, is the recognition problem of such tensor. But once you have a tensor, you can always pixelate it and picturize it. At the end of the day, it's doing this because it's just image processing in algebraic geometry.
Now, do you mean to say every problem in algebraic geometry is an image process?
Almost.
Or is an image processing problem, or just problems involving invariance or image processing, or even broader than that?
Well, I think I'm beginning. It is really more broad. I think at some level, I think in my view, I try to say bottom up mathematics is language processing, and top-down mathematics is image processing.
Interesting.
Of course, this is, you take with a caveat, but of course, at some level, there is truth in what I say. Of course, it's an extreme thing to say, but in terms of what mathematical discovery is that you're trying to take a pattern in mathematics. So in algebraic geometry, which is a perfect example, you can pixelate everything, and you can just try to see certain images have certain properties, and so you're image processing mathematics. Whereas bottom up, you're building up mathematics as a language. So it's language processing. And of course, all of this will be useless if you can't actually get human readable mathematics out of it.
Right.
So this is the first surprise, the fact that it's even doing it at all to a certain degree of accuracy. Now we're talking about accuracies like it's been improved to like 99.99% accuracy in these databases. But that's the first level. That's the first surprise. The second surprise is that you can actually extract human understandable mathematics from it, and I think that's the next level surprise. So the memorization conjectures, this beautiful work in DeepMind that Jody Williamson's involved in this human guided intuition, you can actually get human mathematics out of it, and that's really quite something. So maybe that's a good point to break for part 2, which is an advertisement of here is like we've gone through many things about what mathematics is, and to how I got this through doing this interaction between algebraic geometry and string theory, and then a second part would be how you can actually extrapolate and extract mathematics, actual conjectures, things to prove from doing this kind of experimentation, which are summarized in these books. I keep on advertising my books because I get £50 per year of what do they call it? Royalties, so I don't have to sell my liver for my kids. But it's kind of fun. It's a complete. Academic publishing is a joke, right? You get like £100 a year because you don't actually make money out of it. Right. But maybe that's a good place to break. And then for part 2, how we try to formulate what the Birch test is for AI, which is sort of the Turing test plus. And because the Birch test is how to get actual meaningful human mathematics out of this kind of playing around with mathematical data.
Mm-hmm. I see 2 of your sentence that will be these maxims for the future will be that machine learning is the 22nd century's math that fell into the 21st. So this machine learning assisted mathematics, or that the bottom up is language processing and then the top down is image processing.
Yeah.
I like those 2.
Yeah.
Anyone who's watching, if you have questions for Yang Hui for part 2, please leave them in the comments. Do you want to give just a brief overview?
Oh yeah, sure. So I'm going to talk about what the Birch test is and which papers so far have gone, how close they've gone to the Birch test, and then I'm going to talk about some of the more experiments in number theory, and the one that I really enjoyed doing with my collaborators Lee, Oliver, and Posniakov, which is to actually make something meaningful that's related to the Birch-Swinnerton Dyer conjecture by just letting machine go crazy and finding a new pattern in elliptic curves, which is fundamentally a new pattern in the prime numbers, which is completely amazing. You mentioned quanta earlier. So this quanta feature that featured this one, consider this as one of the breakthroughs of 2024.
Great. And that word murmuration, which was used repeatedly throughout, it was never defined, but it will be in the part 2.
Absolutely.
So I'm looking forward to it.
Sure. Me too.
Okay. Thank you so much.
Thank you.
This has been wonderful. I could continue speaking to you for 4 hours. Both of us have to get going, but
That's
it's
right.
so much fun.
Pleasure.
Don't go anywhere just yet. Now I have a recap of today's episode brought to you by The Economist. Just as The Economist brings clarity to complex concepts, we're doing the same with our new AI-powered episode recap. Here's a concise summary of the key insights from today's podcast.
All right, let's dive in. We're talking about Kurt Jaimungal and his deep dives into all things mind-bending. You know, this guy puts in the hours, like weeks, prepping to grill guests like Roger Penrose on some wild topics.
Yeah, it's amazing using his own background to dig in. Really challenging guests with his knowledge of mathematical physics pushes them beyond the usual.
Definitely. And today we're focusing on his chat with mathematician Yang-Hui He. They're getting into AI, math, where those two worlds collide.
And it's fascinating because it really makes you think differently about how math works, how we do math, and where AI might fit into the picture.
You might think a mathematician's life is all formulas and proofs, but Yang-Hui, he actually started exploring AI-assisted math while dealing with sleepless nights with his newborn son.
It's such a cool example of finding inspiration when you least expect it. Tired but inspired, he started messing around with machine learning in those quiet early morning hours.
So let's break down this whole AI and math thing. Yang-Hui, he talks about 3 levels of math: bottom up, top down, and meta. Bottom up is like building with Legos, very structured, rigorous proofs. That's the foundation. But here's where things get really interesting. It has limitations.
Right, and those limitations are highlighted by Gödel's incompleteness theorems. Basically, Gödel showed us that even in perfectly logical systems, there will always be true statements that can't be proven within that system. It's mind-blowing.
So if even our most rigorous math has these inherent limitations, it makes you think. Could AI discover truths that we as humans, bound by our formal systems, might miss? Could it explore uncharted territory?
That's a really deep thought. And it's really at the core of what makes this conversation revolutionary. It's not about AI just helping us with math faster. It's about AI possibly changing how we think about math altogether.
So how's this all playing out? We've had computers in math for ages, from early theorem provers to AI assistants like Lean. But where are we now with AI actually doing math?
Well, AI is already making some big strides. It's tackling Olympiad-level problems and doing it well, which makes you ask, can AI really unlock the secrets of math?
And that leads us to the big philosophical questions. Is AI really understanding these mathematical ideas, or is it just incredibly good at spotting patterns? It's like that famous Chinese room thought experiment. You could follow rules to manipulate Chinese symbols without truly understanding the language.
Yang-Hui, he shared a story about Andrew Wiles, the guy who proved Fermat's last theorem, trying to challenge GPT-3 with some basic math problems. It highlights how early AI models, while excelling in tasks with clear rules and plenty of examples, struggled with things that needed real deep understanding.
It seems like AI's strength right now is in pattern recognition. And that ties into what Yang-Hui he calls top-down mathematics. It's where intuition and seeing connections between different parts of math are king.
Like Gauss. He figured out the prime number theorem way before we had the tools to prove it. It shows how a knack for patterns can lead to big breakthroughs, even before we have the rigorous structure.
It's like AI is taking that intuitive leap, seeing connections that might have taken us humans years, even decades to figure out. And it's all because AI can deal with such massive amounts of data.
Which brings us back to Yang-Hui. He's sleepless nights, He started thinking about Calabi-Yau manifolds, super complex mathematical things key to string theory, as image processing problems.
Wait, Calabi-Yau manifolds? Those sound like something straight out of science fiction.
They're pretty wild. Think 6 dimensions all curled up, nearly impossible to picture. They're vital to string theory, which tries to bring all the forces of nature together. Now, mathematicians typically use these really abstract algebraic geometry techniques for this. But Yang Hui, he had a different thought.
So instead of equations and formulas, he starts thinking about pixels.
Yeah, like taking a Calabi-Yau manifold, breaking it down into a pixel grid like you do with an image. He's taking abstract geometry and turning it into something a neural network built for image recognition can handle.
That is a radical change in how we think about this. It's like he's making something incredibly abstract tangible, translating it for AI. Did it even work?
The results blew people away. He fed these pixelated manifolds into a neural network, and it predicted their topological properties really accurately. He basically showed AI could do algebraic geometry in a whole new way.
So it's not just speeding up calculations, it's uncovering hidden patterns and connections that might have stayed hidden, like opening a new way of seeing math.
And that leads us to the big question. If AI can crack open complex math like this, what other secrets could it unlock? We're back. Last time we were talking about AI not just helping us with math, but actually coming up with new mathematical insights, which is where the Birch test comes in.
It's like, can AI go from being a supercalculator to actually being a math partner?
Exactly. And now we'll look at how researchers like Yang Hui He are trying to answer that. Remember, the Turing test was about a machine being able to hold a conversation like a human. The Birch test is a whole other level. It's not about imitation. It's about creating completely new mathematical ideas. Think about Brian Birch back in the 60s. He came up with this bold conjecture about elliptic curves just from looking at patterns in numbers.
So this test wants AI to do similar leaps, to go through tons of data, find patterns, and come up with conjectures that push math forward.
Exactly. Can AI, like Birch, show us new mathematical landscapes?
That's asking a lot. So how are we doing? Are there any signs AI might be on the right track?
There have been some promising developments, like in 2021, Davies and his team used AI to explore knot theory.
Knots, like tying your shoelaces. What's that got to do with advanced math?
It's more complex than you think. Knot theory is about how you can embed a loop in three-dimensional space, and it actually connects to things like topology and even quantum physics.
Okay, that's interesting. So how does AI come in?
Well, every knot has certain mathematical properties called invariants. It's kind of like its fingerprint. Davies' team used machine learning to analyze a massive amount of these invariants.
So was the AI just crunching numbers? Or was it doing something more?
What's amazing is the AI didn't just process the data, it actually found hidden relationships between these invariants, which led to new conjectures that mathematicians hadn't even considered before. Like the AI was pointing the way to new mathematical truths.
That's wild. Sounds like AI is becoming a powerful tool to spot patterns our human minds might miss.
Absolutely. Another cool example is Lampel and Charton's work in 2019. They trained AI on a massive data set of math formulas.
And what did they find?
Well, this AI could accurately predict the next formula in a sequence, even for really complex ones. It was like the AI was learning the grammar of math and could guess what might come next.
So we might not have AI writing full-blown proofs yet, but it's getting really good at understanding the structure of math and suggesting new directions.
And that brings us back to Yang Hui He. His work with those Calabi-Yau manifolds, analyzing them as pixelated forms, that was a huge breakthrough. Showed that AI could take on algebraic geometry problems in a totally new way.
Like bridging abstract math in the world of data and algorithms.
Exactly. And that bridge leads to some really mind-bending possibilities. Yang Hui, he and his colleagues started exploring something they call murmuration.
Murmuration. Like birds.
It's a great analogy. Think of a flock of birds moving together like one. Each bird reacts to the ones around it, and you get these complex, beautiful patterns.
Right, I get it. But how does that relate to AI and math?
Well, Yang Hui, he sees a parallel between how birds navigate together in a murmuration and how AI can guide mathematicians towards new insights by sifting through tons of math data.
So the AI is like the flock, exploring math and showing us where things get interesting.
Yeah, and they've actually used this murmuration idea to look into a famous problem in number theory, the Birch and Swinnerton-Dyer conjecture.
That name sounds a bit intimidating. What's it all about?
Imagine a donut shape, but in the world of numbers. These are called elliptic curves. Mathematicians are obsessed with finding rational points on these curves, points where the coordinates can be written as fractions.
Okay, I'm following so far.
The Birch and Swinnerton-Dyer conjecture basically says there's this deep connection between how many of these rational points there are and a specific math function, like linking the geometry of these curves to number theory.
Things are definitely getting complex now.
And it's a big deal in math. It's actually one of the Clay Mathematics Institute's Millennium Prize problems. Solve it, you win $1 million.
Now that's some serious math street cred. So how did Yang Hu He's team use AI for this?
They trained an AI on this massive data set of elliptic curves and their functions. The AI didn't actually solve the whole conjecture, but it found this new pattern, this correlation that mathematicians hadn't noticed before.
So the AI was like a digital explorer, mapping out this math territory and showing mathematicians what to look at more closely.
Exactly. This discovery, while not a complete proof, gives more support to the conjecture and opens up some exciting new areas for research. It shows how AI can help with even the hardest problems in mathematics.
It feels like we're on the edge of something new in math. AI is not just a tool, it's a partner in figuring out the truth. What does all this mean for math in the future?
That's a great question, and it's something we'll dig into in the final part of this deep dive. We'll look at the philosophical and ethical stuff around AI in math. We'll ask if AI is really understanding the math it's working with, or if it's just manipulating symbols in a really fancy way. See you there.
Welcome back to our deep dive. We've been exploring how AI is changing the game in math, from solving tough problems to finding hidden patterns in complex structures. But what does it all mean? What are the implications of all of this?
We've touched on this question of understanding. Does AI really understand the math it's dealing with, or is it just a master of pattern matching?
Yeah, we can get caught up in the cool stuff AI is doing, but we can't forget about those implications. If AI is going to be a real collaborator in mathematics, this whole understanding question is huge.
It goes way back to the Chinese room thought experiment. Imagine someone who doesn't speak Chinese has this rule book for moving Chinese symbols around. They can follow the rules to make grammatically correct sentences, but do they actually get the meaning?
So is AI like that, just manipulating symbols in math without grasping the deeper concepts?
That's the big question, and there's no easy answer. Some people say that because AI gets meaningful results, like we've talked about, it shows some kind of understanding, even if it's different from how we understand things. Others say AI doesn't have that intuitive grasp of math concepts that we humans have.
It's a debate that's probably going to keep going as AI gets better and better at math. Makes you wonder how it's going to affect the foundations of mathematics itself.
That's a key point. Traditionally, mathematical proof has been all about logic, building arguments step by step using established axioms and theorems. But AI brings something new: inductive reasoning, finding patterns, and extrapolating from those patterns.
So could we see a change in how mathematicians approach proof? Could we move toward a way of doing math that's driven by data?
It's possible. Some mathematicians are already using AI as a partner in the proving process. AI can help generate potential theorems or find good strategies for tackling conjectures. But others are more cautious, worried that relying too much on AI could make math less rigorous, more prone to errors.
It's like with any new tool, there's good and bad. Finding that balance is important. We need to be aware of the limitations and not rely on AI too much.
Right. And as AI becomes more important in math, it's crucial to have open and honest conversations. We need to talk about what AI means, not just for math, but for everything we do. It's not just about the tech, it's about how we choose to use it.
We need to make sure AI helps humanity and the benefits are shared. That's everyone's responsibility.
A responsibility that goes way beyond just mathematicians and computer scientists. We need philosophers, ethicists, social scientists, and most importantly, the public. We need all sorts of voices and perspectives to guide us as we go into this uncharted territory.
This has been an amazing journey into the world of AI and math. From sleepless nights to those mind-bending manifolds, we've seen how AI is pushing the boundaries of what's possible.
And as we wrap up, we encourage you to keep thinking about these things. What does it really mean for a machine to understand math? How will AI change the way we prove things and make discoveries in math? How can we make sure we're using AI responsibly and ethically in our search for knowledge?
These are tough questions, but they're worth asking. The future of mathematics is being shaped right now, and AI is a major player. Thanks for joining us on this deep dive. We'll catch you next time, ready to explore some other fascinating corner of the universe of knowledge.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate TOEs, they disagree respectfully about theories, and build as a community our own TOE. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/KurtJaiMungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.